Hello guys, today we are going to review a half-wave rectifier using Multisim, which is an electronic simulation software. Even when we cover this topic in class, this is a trial video because we are transitioning to an online format. In this video today, you are going to see two themes. Number one, I'm going to take you to your workbook for level 2 electronics, and we are going to explore the half-wave rectifier that you already completed in the shop. And number two, we are going to take the same circuit and we are going to use Multisim in order to simulate the circuit that you have already done in the shop, as I mentioned, and be able to obtain the different readings and see the oscilloscope in action. First, let me take you to your book. So this is the same. And like right here, this is the same circuit that you were doing in the shop. First, you can see that we have a center tap transformer, and I'm going to highlight it here. This is a center tap transformer that is 28 volts. The center tap transformer is connected to a diode. So we can say that line 1 is connected to the diode, and that our line 2 is connected to the other side of the load. Also, in the shop, you connected the oscilloscope in order to be able to see and measure the results of your sine wave. So in this case, we have the input sine wave. That part of the sine wave is positive, as we have discussed before, and this other part of the sine wave is negative. When the diode is connected positive to positive, it's going to behave as a forward bias diode, and it's going to conduct that portion of the signal. It's going to be behaving as a closed switch. However, when the signal becomes negative, the diode is going to be reverse biased, and it's going to behave as an open switch, and it's going to block the signal, which is going to be displayed on the screen of the oscilloscope as a flat line. That way, we are going to be able to obtain half-wave rectification by using just one diode connected in series with our light bulb. If we want to know what's going to be the output voltage, we have that E average, it's equal to E RMS times 0.45. I want to remind you that ERMS, it is the same thing as the effective voltage of your sine wave. This is the same thing. While this portion here, which is called pulsating DC, is going to be our rectified voltage, and that is our average voltage. And as I mentioned, we are going to get the value of that signal by multiplying our 28 volts, which is our applied voltage, times 0.45. That will be equal to 12.6 volts. Now, this 12.6 volts that we have right here is a DC voltage. Let's verify with the simulation software, which is Multisim. So now I'm going to share my Multisim screen so we can verify to see if this holds true. Right here, you can see that we have our central tap transformer. I decided to include a switch. And at this point in time, we have two different probes. One of them is going to indicate the effective value of the sine wave right before the diode. And the other probe is going to indicate the voltage, the rectified voltage right after the diode. Please notice that here I have two different voltages. We are going to be able to see the DC voltage, which is the effective, which is the, sorry, not the effective, which is the average voltage. And we are going to be able to see also an RMS voltage right there after the diode, which is called the ripple voltage. When we close the switch, we can see that indeed we have 28 volts at 60 hertz. This is the peak-to-peak value. If you don't remember how to calculate this value, please send me a question and I'll remind you. Right here, right after the diode, then we have the same 60 hertz. And then we have a voltage DC, which is equal to 12.1. You can see that the light bulb is working. But here, at the same moment, we can see that we have a ripple voltage, which is equal to 19.2 volts. And still, we can determine what is the peak-to-peak voltage of our rectified voltage. Because as I mentioned before, this is pulsating DC. Anyways, guys, let's look at the oscilloscope. If we look at the oscilloscope here, okay, just give me 1 second here. Right here on the oscilloscope, we can see the same signal that you were able to see in the chart. You can see your halfway rectification. This wasn't a perfect video. However, I wanted to put this out there because I want you to get started reviewing all these topics. And I want to be able to start getting in touch with you and getting together online in order to continue with our theoretical classes. Anyways, have a nice day, and I wish you success in this new process. Thank you very much.